So how do engineers make sure a massive skyscraper doesn't just get blown over in a storm? Well, they do it by taking the raw, chaotic power of the wind and turning it into a precise set of numbers. Let's dive in and see exactly how it's done. I mean, really think about it for a second. These incredible structures are constantly battling the forces of nature. The secret? It lies in a set of engineering rules called the Eurocodes. You can think of them as the ultimate playbook for calculating the true power of the wind.
Okay, so the entire calculation, the whole thing, begins with one really simple question. Where in the world is this building? Because, as you can probably guess, the wind you'd expect in Denmark is going to be a whole lot different than the wind in, say, southern Spain. To make this all feel real, we're going to follow the process for a pretty standard office building located right here in Copenhagen. And as you'll see, this specific location is the absolute key that unlocks the entire calculation. And here it is. This is our starting number, 24 meters per second. This is what's called the fundamental basic wind velocity for Copenhagen, and it's pulled directly from Denmark's official engineering rulebook. Think of it as a baseline storm, a wind speed so strong it's only expected to happen once every 50 years. So we've got our base speed, but that's really just the beginning. I mean, wind acts totally different in an open field than it does in a crowded city, right? And it's obviously a lot stronger at the top of a building than it is down at the street. The next step is to turn that simple speed into a real, tangible force. To do that, we take our base wind speed and we mix in two other key ingredients, the building's height, which for us is 17.1 meters, and the local terrain. Since our building is in a suburban area, all the other buildings and trees around it are going to slow down and stir up the wind. It's not a smooth flow like you get in an open field. Now, when you combine all those inputs, you can calculate something called peak velocity pressure. It sounds complicated, but it's really just the raw kinetic energy of the wind converted into a pressure. Put it this way, it's the maximum punch the wind can pack at the very top of our building. And here is our result, 0.746 kilonewtons per square meter. Now, to put that into perspective for you, that's kind of like having about 165 pounds of force pushing on every single square meter at the top of that building. That is the peak force we have to design for. But this is where it gets really interesting, because wind is tricky. It doesn't just push on a building like a giant hand. Nope, it swirls and eddies, creating these complex zones of pressure and suction all over the surface. So the next step is to map these zones out. Essentially, you've got two things happening at once. On the front face, the wind is pushing directly in. We call that positive pressure. But as that wind whips around the corners in the back, it creates this powerful vacuum effect, pulling the walls out. That's suction, or what we call negative pressure. And this table just illustrates brilliantly how Eurocode handles this. It gives each zone a number called an external pressure coefficient. A positive number, like the plus 0.8 on the front, means it's a push. But a negative number, like that whopping minus 1.2 right on the side edge, means you've got some seriously strong suction going on. All right, we are almost there. We have the raw power of the wind, and we know how it's distributed on the outside of the building. But there's one last absolutely critical piece of the puzzle we need to consider. Exactly. You know, buildings aren't perfectly sealed boxes. They've got windows, doors, vents, all sorts of little openings. This means pressure can also build up on the inside, and that internal pressure can have a massive impact on the final forces the walls actually feel. So here's the crucial part. Engineers have to check for the worst case scenario, always. They calculate what happens if the internal pressure is pushing outwards, and then they calculate what happens if it's creating a suction inwards. Whichever one of those creates a bigger total force on the wall, that's the one they have to design for. And you know what? The math itself is beautifully simple. The final net pressure on any surface is just the difference between the pressure on the outside and the pressure on the inside. That's it. That tells you the true force the wall or the window or a cladding panel has to be able to resist. And here it is, the final verdict. After we combine all the factors, these are the design pressures. So you can see the front face has to resist a push of about 0.82 kilonewtons per square meter. But look at the side edge, zone A. It has to withstand a massive suction force of over 1 kilonewton per square meter. That's a force literally trying to rip the cladding right off the building. So let's do a super quick recap. It's really a four-step journey. First, you start with a map to get your base wind speed. Second, you calculate its power based on the building's height and its terrain. Third, you map all those external pressure and suction zones. And finally, you add in the internal pressure to find your final design forces. And that brings us to the single most important takeaway from all of this. You see, the Eurocode is a framework, it's a guide, but the specific, legally binding numbers, like that base wind speed we started with, are found in each country's own rulebook called the National Annex. You absolutely have to use it. So the next time you see a skyscraper standing tall against a howling storm, you'll know about the incredible journey of calculation that makes it possible, from a simple spot on a map to the final powerful forces. And the one rule engineers live by, always check the National Annex. Thanks for tuning in.